In the name of Allah, the most beneficent, the most merciful. Assalamu alaikum. I am Kashiful Khair from BS Chemistry Department and my ID is 018. Today I am here to present the topic of organic chemistry, which is named reaction and its detail. So, basically a named reaction is a chemical reaction which is named after its discoverer or developer. In some cases, the person whose name is associated with the reaction was not to first discover the reaction, but instead managed to popularize the reaction. So, reaction can also simply describe the reaction type, often by using the initial or referring to structural feature of that reactions. There are thousands of named reactions in organic chemistry, out of which 5 I am going to explain in this presentation. And these are Williamson synthesis, Des-Martin oxidation, Nigishi cross-coupling reaction, Stoyl cross-coupling reaction, and the Ullmann reaction. So let's see what is Williamson synthesis reaction. Basically, this reaction was developed by Alexander Williamson in 1850. Moving towards its introduction, the Williamson ester synthesis is the easiest and the fastest way to create ethers. Basically, it is a reaction that converts alcohols into ether. The first step is forming the conjugate base of alcohol, which is called as alkoxide, and alkoxide is produced by reacting alcohol with sodium metal. Alkoxide consists of the conjugate base of an alcohol and are comprised of an R group bonded to an oxygen atom. They are often written as RO, where R is the organic substituent, as we can see in the given example. Ether are also prepared by SN2 reactions. Basically, ethers can be synthesized in standard SN2 condition by coupling an alkoxide with the alkyl halide. The alcohol that supplies the electron-rich alkoxide can be used as a solvent, and the solvents are DMSO, which is stand for dimethyl sulfoxide, and HMPA, hexamethyl phosphoric triamide. For example, we can see here is an alkoxide ROS and A+, and with alkyl halide Ri, and which it will give us ROR, which is the ether. Next, moving towards the mechanism of the reaction. Basically, alkoxide ion RO ion will act as a nucleophile and it will attack on the electrophilic carbon with leaving group, which is in most cases is alkyl halide. So after that, an ester will be produced. The leaving site must be a primary carbon because secondary and tertiary leaving sites generally prefer to proceed as an elimination reaction. So this reaction doesn't favor the formation of bulky ethers like di-tertiary butyl ethers due to steric hindrance and predominant formation of alkenes instead. Moving towards the limitation of the Williamson synthesis. Basically, alkali phenoxide may undergo C alkylation in addition to accepted O alkylation. So it is a great limitation of Williamson synthesis. Basically, C alkylation is a process of the formation of carbon-carbon bond. For alkylation at carbon, the electrophilicity of alkyl halide is enhanced by the presence of Lewis acid. While on the other hand, O alkylation is the alkylation of alcohols involve alkylating agent, which is an alkyl halide. Alcohol alkylate to give ethers in O alkylation. The second limitation of Williamson synthesis is that this process for preparing ether is too limited to be of any practical value for synthetic organic chemists. Next are the applications of Williamson synthesis reaction. Basically, Williamson synthesis reaction is widely used in both laboratory and industrial synthesis. This reaction is significant in the organic chemistry history as it has helped to prove the ether's structure. It is the simplest and most popular method of preparing ethers. We can prepare symmetrical and asymmetrical ethers by using this process. The intermolecular reactions of halohydrin in particular gives epoxide. Ethers are quite unreactive and therefore are desirable solvents for fats, oils, waxes, perfumes, resins, dyes, gums, and hydrocarbons. And vapors of certain ethers are used as insecticides, miticides, and fungicides for soil.